Okay, so let's continue from previous session. So let's take a look at this example 5.3, power of WGN. Okay, so now we consider the PDF of 5.1 with A equal to 0 and sigma square as the unknown parameter. Then let's write out the probability density function of data and sigma square. That is equal to this 1 divided by 2 pi sigma square n divided by 2 multiplied by exponent of 1 over 2 sigma square summation x square multiplied by 1. So let's observe this equation. We will see that I think the one thing is you are expecting g of t of x and sigma square multiplied by h of x. So we have to observe carefully and then make the data x square n into a single t of x, meaning that if you see some terms with data, you want to put it into a single function of data as much as you can so that you can write it out as g of t of x and sigma square. I think that will be kind of the objective we want to do. Okay, so we observe there is a sigma square here. So we uh, intend to make this term separately, and then there's a summation x squared. So you want to make this separately also. So if you separate sigma square and this, you will see this as t of x, and this as sigma square, which is the parameter. And then you can multiply by arbitrary constant 1, then you get a h of x. H of x can be uh, a constant, right? Any function can be a constant. So h of x is a constant 1. That has no problem. So again, it is immediately obvious from the factorization theorem that p of x of this is a sufficient statistic for this. Okay, so let's look and review it. We see that uh, p of x in this form is a sufficient statistic for A. If in this equation A is 0, which is a known constant, and then sigma is an unknown, then you see the sufficient statistic is a function of data, but in different form. You see this is summation of x, and this is summation x squared. So you see that sufficient statistic always corresponds to a specific parameter. It's unique with that parameter. 所以我用中文稍微解释一下，就重复解释一下，因为这个观念稍微比较抽象一点的哈。就是如果你的 parameter 是 a 的时候，那你的 summation x 就是对 a 的 sufficient statistic。如果你的 parameter 是 sigma square 的时候，那你的 sufficient statistic 就是 summation x square。也就是说 sufficient statistic 跟 parameter 是对应关系的，而且是独特的，并不是说有一个 sufficient statistic， 然后它对所有的 parameter 都是 sufficient， 这不会是这样子的思考，就是这样子的想法是不合理的。 我们想这个事情的方式一定是要一个 sufficient statistic 对独特的对应着某一个 parameter， 通常会是这样子的状况。那有没有一组 data 是对很多 parameter 都是 sufficient 呢？会不会呢？也有可能，也有可能。好，我举例来讲，有没有一组 sufficient statistic 对 sigma square 是 sufficient， 也对 A 是 square， 也对 A 是 sufficient 呢？有的，就是我们先前讲那个 S1， 我们再回忆一下 S1。如果你保留 S1， 那你就保留了所有的原始资料。那原始资料具有的资讯量一定是最大的，所以我们可以说，刚才那个 S1， 它对 A 是 sufficient， 它对 sigma square 也会是 sufficient。这个是会发生，但是很少见，会发生的事情，但是很少见。通常会是一个 sufficient statistic 对一个 parameter 的关系。好 ，Okay, so now let's turn to another parameter that is the phase of sinusoid. So let's recall previous example in which we wish to estimate the phase of a sinusoid embedded in white Gaussian noise. So the data model is x of n equal to a cosine 2 pi f0 n plus phi plus w n. And n is a multiple sample, so it is from 0, 1 all the way to n minus 1. So here, the amplitude A and frequency f0 of the sinusoid are known. In other words, we treat this A and f0 as known. So they are not parameter to be estimated. So let's be clear about this. A and f0 is not the parameter to be estimated. The parameter to be estimated is the phi here. And also the sigma square for this W is known. Okay, so they are not parameter to be estimated. Okay, so if we write a PDF, then it has to be P of X phi equal to Gaussian distribution. You write it out, right? This is a Gaussian distribution with this term as the mean. Let's stop for a few seconds and think about it. You have this plus a Gaussian, then this constant term. In theory, that will be the mean. So it will be the mean in the Gaussian distribution. And then this is the factor for Gaussian distribution, exponent and summations, etc. Those things are standard Gaussian, standard Gaussian formulation. So you have P of X phi written out in the Gaussian form. Then the exponent may be expanded as this, because you just expand this second order polynomial, right? It's a second order polynomial. So you write it out, you get this summation square minus 2a summation of this and summation a square cosine square. All right, and then write this out and write this out, and then this term is written here. So how do we go from here to here? What happens here is you use a trigonometric identity 三角函数的公式，记得吗？三角函数有一个公式是 cosine a 加 cosine， 不是，是 cosine A 加 B， 记得这个公式吗？好，那我讲一下哈，就是 cosine A 加 cosine 不是，对不起，cosine A 加 B 等于 cosine A 乘以 cosine B 加上减掉 sin A sin B， 所以如果你带这个公式的话，你就得到这个项。Okay, you have still 2a, right? You have 2a, x summation x, right? And then cosine 2 pi f0 here, cosine phi. You have sine 2 pi f0n, sine 2 pi f0n, and then sine phi. So this term comes from this term. Okay, so so you have this. You have this that goes to this, and this. Okay, and this term goes to here. This term goes to here. Okay, so in this example, uh, you see what happened here is it seems like we have trouble, right? What trouble? As I mentioned in this case, we say that P of X is the only way that you mix with theta. You cannot have theta to mix with theta individually. Now you have cosine phi, it mixes with this x through this, and then it mixes with x through this sine. So it doesn't seem like we have this form fitting into this, right? So we have a little bit of trouble here. Okay, so we have to see that in this example, it does not appear that the PDF is factorable as required by the Neyman feature. So no single sufficient statistic exists. Okay, so in this case, if we like to be very strict, take a very strict perspective, then we will say that there will be no single sufficient statistic. Okay, but we take another perspective. Okay, so here what follows is we try to take another perspective. P of x phi equal to this exponent of this multiplied by this. Okay, so that will be what? That will be you write this out, right? You write this term into here, right? This term it existed at the exponent. Remember this. This exists here, which is at the position of an exponent. Okay, so you write this out, you get this exponent, and then the rest is put into this form. So you have a squared cosine square here, right? You have this goes to here, and then you have this and this goes to here. And what happens is you try to write this as T1, write this as T2. So you get T1 equal to this, T2 equal to this. Okay, so let's just take a few seconds and watch the details. You have T1 equal to this and multiplied by cosine. So you have T1 multiplied by cosine. You have P2 equal to this multiplied by sine. So you have P2 multiplied by sine. Okay, so now then we will be able to write this into g of P1x T2x and phi, right? In other words, the phi interact with data through what? Through T1 and T2 jointly. OK，注意这个字眼 jointly。OK，jointly。phi 和 x 的互动，在这个方程式里面的互动，就是透过 T1 跟 T2 共同的互动，共同。所以So we will be able to write this into a GT1, GT2 phi, and then summation of data only. Then write this into H. Okay. So let's see what happens next. By a slight generation of the Neyman-Fisher's theorem, we will say that T1 and T2 jointly sufficient statistic. They are jointly sufficient. So if you have T1 and T2, then it will be jointly sufficient for phi. That's what we are saying for this jointly sufficient statistic. Okay, but no single sufficient statistic exists. You have to do two things, which is T1 and T2, and then if you maintain T1 and maintain T2, then you have sufficient information about phi. But if you have only one number, which is maybe T1 or T2 only, then it's not sufficient. Okay, so I think that will be the idea of joint sufficiency. Okay, so the concept of jointly sufficient statistic is a simple extension of previous definition. The R statistics are jointly sufficient. Notice this. R statistics of these things are jointly sufficient statistics if the conditional PDF does not depend on theta. But it has to be jointly, not one of them. Okay, not one of them is not sufficient. Some of them are not sufficient. Part of them are not sufficient. Then it has to be all of them jointly, then it will be sufficient. Okay, so let's see it this way. So it's, if jointly and all of them together does not depend on theta, then it's jointly sufficient. So that is a kind of a generalization. So you can see this. You have this P and that. Okay, they are jointly sufficient statistic. All right. So we will be saying that this is like most mathematics. If you have something, then there will be another thing that is jointly sufficient. Things like those. Okay, so